Okay, we're continuing on here, chapter 15, I think. So last time we got into really solution stoichiometry, and remember, pretty much this is another sort of stoichiometry sort of conversation we've had, but really all stoichiometry, rather if it's regular sort of stoichiometry with grams and moles, stoichiometry involving gases, or even stoichiometry involving solution, they pretty much all still follow those same four steps. No matter when you're doing stoichiometry, you always need a balanced equation. You always need to convert to moles, whatever they give you. You also always, when you're doing a stoichiometry problem, determine, is it a limiting reagent type of situation or not? You do need to do the mole to mole relationship from the equation. And lastly, convert those moles to whatever unit you're looking for. So in terms of solution stoichiometry, pretty much the main difference is there are really the two steps where it usually is a difference, and that is kind of your step number two or step number four here. And the main difference is, again, instead of a traditional sort of stoichiometry problem where we go from grams to moles, again, using the molar mass, very often in solution stoichiometry, we're using molarity here, and we're going to be solving for moles, and that is liters times the molarity. So in that sort of second step, a lot of times with solutions, you're usually given the concentration, perhaps the volume that you're using, and that's basically how you're going to get moles rather than going to the periodic table and using the molar mass. Now, at the end of the problem as well is also usually a place where molarity also sort of comes into play. Traditionally, in a traditional stoichiometry problem, we go a lot of times moles back to grams, also using the molar mass to do so. But with solution stoichiometry, you will have moles at this point, and really you could go in a couple of directions. If you know the volume, you could actually calculate the molarity because at that point you'll know the moles and the liters. Uh, you may also, if you know the molarity and you know the moles, you could actually again use molarity here and instead solve for something like the liters. So there's a couple different sort of outcomes when you get to sort of that last step, using molarity on the back end. Thank you. I would say it is very, very common to sort of use molarity and volume in both of those locations a lot of times with solution sort of problems, stoichiometry problems, and especially with titration problems that we were talking about as well. So remember that in a titration, which is really just a solution stoichiometry problem, the actual process of a titration is what you did in that experiment. Once again, we take something like a burette and we put something in it. It could be a base, could be an acid, and on the other side there or underneath it, we have basically the opposite thing. So we could do an acid there, and you can switch it around again. You could do your acid up in the burette and a base down on the bottom. We typically put in there on the bottom into our solution an indicator which changes color when we reach what is basically considered the end of the reaction in a typical titration, and that is the equivalence point. And in the equivalence point of a titration, especially an acid-base titration, that's when the moles of the acid will equal the moles of the base. So that's the exact point where essentially you've used up everything you started with, because in this type of reaction, we're basically taking an acid plus a base and we're going to create a salt and water. So like the titration you did, took some hydrochloric acid, you reacted with some sodium hydroxide. It gave you a little sodium chloride. And I'll go on the other side here. It gave you some water as well. And that is our salt, obviously, here, which is just an ionic compound. And obviously, that H2O over there is our water. in that case. So when you reach the equivalence point, pretty much both of these guys end at zero. You got pretty much none of that left over once you reach the equivalence point. They've completely basically neutralized each other. And that is sometimes how problems are worded as well when you kind of read them. They may not say titration, but they'll talk about like neutralizing an acid with a base or how much to neutralize it. And that's usually the sort of spot we were talking about is the equivalence point here. Again, it is really when you're doing some type of calculation, and when we do a titration, we typically have a known solution and we have an unknown solution when we're doing some type of titration. And the known solution is something much like the name implies. You know everything about it. You know the molarity, you know the volume that's used. So that allows you really to figure out the moles of the known solution. For the unknown solution, again, you may just know a couple of things about it. You may just know the volume of it, and maybe you want to sort of figure out what is the molarity of it, and that is where the stoichiometry comes into play. So there's always a solution in a titration that is a known solution that allows you to use that information and basic stoichiometry to figure out something about the unknown solution, be it the molarity. Maybe you do know the molarity, and maybe you want to know the volume or how many moles you used of it along the way. Any questions on that there? All right, then why don't we try this one here? I think maybe wait, let's try this one. I think we did that one, if I'm not mistaken. Yeah, I think we did that one. So I think let's do this one here. All right, so if in a titration it requires 63.5 milliliters, 0.375 calcium hydroxide to reach the equivalence point in a titration of 95.5 milliliters of hydrobromic acid, what is the molarity of the hydrobromic acid? So take a few moments here, work through your kind of 4 steps, and see what you come up with. Okay, so let's take a look, see how you're doing. So obviously here we're doing a titration where you are reacting calcium hydroxide with hydrobromic acid. So we do need obviously an equation here. Oops, come back. All right, so we need our equations. So calcium hydroxide, calcium is +2, hydroxide is -1. So when we put it together, we get a little CaOH2. Going to react with hydrobromic acid. Hydro means there is no oxygen in it. So that is HBr. Remember that pretty much all acid-base reactions are double displacement reactions. Basically got, again, a positive guy, negative guy, positive, negative. So once again, we just want to put it together correctly. So calcium is that. Hydroxide is that, OH minus, H plus for the acid, and Br minus. So once again, we're going to switch partners here to get what's on the other side. We want to put them together in the proper way to equal 0. So CaBr2 in this case, as we'll need 2 of those, plus some water. And again, remember, we don't want to sort of try to balance it as we're writing the equation. We just want to get the proper formulas down. Once we do, now we can kind of go back and balance everything up. And just got to clean up some of this here. And it looks like we'll need some 2s here, perhaps. We'll need a 2 there. And I think we will then need a 2 there, I think. And now we should be balanced at that point. First off, any questions on the equation there? All right, now that we sort of have our working equation, we can kind of take the information that's given to us so we can do a little analysis of where we need to go and what we're starting with. So for the calcium hydroxide, we have 63.5 milliliters. We do have the molarity of 0.375. For the hydrobromic acid, we do have a volume of 95.5 milliliters, and we are looking for the molarity here. So the molarity is our moles per liter. We actually do have part of that, which is The 95.5 milliliters just needs to be converted to liters. The moles part we are missing, and the moles part is going to come from the stoichiometry. We could definitely get moles from this information here. So that is where we're going to start with. And again, we're going to use the information from calcium hydroxide, which in this particular titration would be kind of our known solution. We know everything about it. And obviously, the HBr here is really our unknown solution that we're trying to figure something about it out, which would be the molarity in this case. So step number 2 is we're going to take what they gave us basically and convert it into moles. Remember that when you are using volume and molarity by itself, not in the dilution equation, you do need to make sure you convert your volume to liters. So we definitely want to do that. So we're going to take our 63.5 milliliters. We're going to convert it to liters. There's 1,000 milliliters in a liter. That will give us 0.0635 liters. That's going to work good with our molarity. Also, something we talked a lot about, which is when you're doing a calculation, you should probably take a dimensional analysis approach, especially with molarity. You should kind of convert that big M into both units so you can kind of see them. And that is basically this number right here showing both of the units. And now we can just use it like a normal sort of conversion factor. Opposites cancel, liters are on top, so liters on the bottom so that they cancel out of our calcium hydroxide here. Liters will cancel, and we will end up with here 0.0635 times 0.375. I'll end up with 0.02381 moles of calcium hydroxide. Any questions up to there? All right, so remember, we're really not interested in calcium hydroxide here. We're interested in the hydrobromic acid. So that's really where the stoichiometry part of it's going to help us out. We can now do really our third step here. And obviously, in this case, this was not a limiting reagent type problem because obviously we are solving for a reactant. So definitely we don't have enough information about both reactants. So step number 3 is just our basic stoichiometry. We're going to go to the equation. We're going to find our two things we're interested in, which are these two things. And from the equation, we can see we have 1 mole of calcium hydroxide. Pretty much gives us reacts with 2 moles of HBr. And that's really just a conversion factor to take us from calcium hydroxide to hydrobromic acid. And that's because that's ultimately what we kind of need here. So we will take our number there that I didn't round too much on, I think. Moles of calcium hydroxide. Once again, using our stoichiometry from the equation as a conversion factor, opposites cancel, so 1 mole of calcium hydroxide on the bottom and 2 moles of HBr up on top. The moles of calcium hydroxide cancel there, and we will end up with, looks like 0.047625 moles of HBr. Now, that is, as I mentioned before, really the top part that we need there to calculate the molarity because we already have the volume. Before we do calculate the molarity, we also need to convert that volume into liters as well. So we got to make sure it's always liters there with molarity. So the last thing we're going to do here is take our fourth sort of step, and we're going to take our 95.5 milliliters, which was the volume of HBr. We're going to convert it into liters. So once again, 1,000 milliliters is a liter. And that's going to give us 0.0955 liters. Now we're ready to calculate our molarity. Our molarity would be our moles, which is above 0.047625. Our volume, 0.0955 liters. And that will get us here, looks like, about 0.499 molar, and that is for our HBr, right? HBr. Any questions on those steps there? So again, hopefully you can kind of see the same pattern that we've seen before in pretty much all stoichiometry problems, regardless if they're regular grams and moles, if they're sort of gas law or solution, we have basically our same four steps that we do here. Balance equation, convert to moles, mole to mole relationship, and moles to some other unit. Any questions on that there? All right, then let us continue on then. The next sort of thing we're going to talk about is another sort of unit of concentration, which truthfully not used all that much these days in sort of chemistry labs in school and stuff like that. But if you buy chemicals or stuff like that in industry, they still use it. And that is normality. And normality is abbreviated much like molarity. It's actually abbreviated with an N rather than an M. And N obviously stands for normality. Normality is, like I said, another concentration unit that is sometimes used, and it's oftentimes used with acid and bases. I'm trying to think. Sometimes they'll have it on the label of like the sodium hydroxide or hydrochloric acid that we were using in that lab. I can't remember if it was on there or not. But it deals with how much H plus and OH minus there is available in an acid or a base reaction. And an equivalent of acid is the amount of acid that can furnish 1 mole of H plus ions, while the equivalence of a base is how much base could basically produce OH minus ions. And another term that's sometimes used with acid-base titration is what's known as equivalent weight. And unlike molar mass, equivalent weight is how many grams there are in one equivalent, and that is grams per equivalence is the equivalent weight. Now, how do we know, how many equivalents something has? It has to do with really the H pluses that will come off. So, for example, if you had something like hydrochloric acid, that would break apart into H plus and Cl minus. You basically get 1 H plus per HCl, and in 1 mole of HCl, you would get one equivalent. And because you get basically 1 H plus that comes off, as opposed to, say, hydrosulfuric acid, when that breaks apart, you get 2 H pluses and a sulfide. And that means in 1 mole of this acid, you would get two equivalents, basically because you're producing 2 H pluses. And it could also do it with bases as well, and it just works with hydroxide, like the one we just did there in that last one. That was calcium hydroxide. When that breaks apart, you get a calcium ion and a couple of hydroxides. And that means in 1 mole of calcium hydroxide, you'll produce two hydroxides, and that will give you basically two equivalents of hydroxide. So the amount of hydroxide or the amount of H plus that can be produced by an acid or base will give you basically how many equivalents you would get. And again, grams per equivalent is the equivalent weight, which is sometimes used for acids and bases. Questions on that there? All right. So, as I mentioned, a reminder that some strong acids like HCl, nitric acid, sulfuric acid. Remember our list of strong acids. It's basically those guys there. We could add perchloric acid to it, hydrobromic acid, hydriodic acid. Those are pretty much your list of strong acids. Common strong bases, sodium hydroxide, potassium hydroxide. Remember that if you look on the periodic table for bases, lithium, sodium, potassium, hang a right-hand turn to calcium, strontium, and barium. If you hook any of these guys up in group 1 or 2 on the periodic table with hydroxide, These are typically where a lot of our strong bases come from, like we see here, sodium hydroxide, potassium hydroxide. So as I mentioned before, because HCl can only furnace one H plus, 1 mole of it will give you 1 mole of H plus ions, and that will essentially give you one equivalent. Now, because of that, the molar mass will actually equal the equivalent weight, and that is because the molar mass would be grams per mole. And because you essentially will have 1 mole of HCl will give you one equivalent, the moles will cancel. It's a one-to-one relationship. You'll end up with grams per equivalent. So the molar mass in this case in grams per mole and the equivalent weight will actually be the same number because it's a one-to-one relationship between those two. So both of those numbers will be the same. But if you did it for something like, say, sulfuric acid or something like we just saw there, hydrosulfuric acid, because it's not a 1-to-2 relationship, it will be different. So if, say we did this for H2S, which we saw 1 mole of it will give us two equivalents. If we had the molar mass of H2S in grams per mole and use that sort of conversion factor, 1 mole will give us two equivalents. That means that the moles will cancel, and essentially our equivalent mass or equivalent weight will actually be half of what the molar mass is because we would be dividing by 2 in this case. So it actually go down by half. So if it's monoprotic or has one equivalent, the molar mass and equivalent weight will be the same number. But if it is something that is not a one-to-one relationship, the equivalent weight and the molar mass will be different. This will be about half the molar mass. Any questions on that? You could also see that is obviously our conversion factor to go between those two, the moles and the equivalents. So let's take a look at this arsenic acid, H3ASO4. We want to calculate the equivalent weight in grams per equivalent of it. So really the first thing that we would want to do in this situation is we would want to figure out the molar mass is probably a good thing. So let's go through the molar mass here. So that is going to be 3 times 1.008 grams per mole from the periodic table, plus our arsenic. It's like 74-ish, I think. 74.92, I think. 74.92 grams per mole for the arsenic. Obviously, that's our hydrogen, our arsenic. And then we would have 4 times our 16 for our oxygens. And that's going to give us a molar mass here of 3 times 1.008 plus 74.92 plus 4 times 16 gives us 141.9 grams per mole. Now, that is the molar mass here of it, which is 141.9 grams over moles. We could also use the formula here to help us understand how many equivalents we should get. And looking at that formula, you hopefully should be able to see it pretty much, but this will break apart into 3 H pluses and ASO4 3 minus in this case. And from that, because it has the ability to produce 3 H pluses and 1 mole of arsenic acid, we will get 3 equivalents here. And again, that's because of the 3 H pluses. And we can basically use that as a conversion factor here. So if I take the molar mass in grams per mole, and I take that relationship we just saw there, the moles will cancel, and we will end up with an equivalent weight of 47.3 grams per equivalent here. And as you can see here, basically the equivalent weight is about 3 times less than the molar mass here because of that. Any questions on that there? So normality, as I mentioned, is a common unit that is sometimes still used a little bit. And instead of moles per liter, it is equivalents per liter. So normality is equivalents per liter. Again, not to be confused with the most common unit of concentration, which is molarity, which is moles per liter. So really the difference here is the top. And that is what we could get from obviously what we just did there from the formula and figure out how many moles and how many equivalents we would have. So if we had a 2.5 molar sulfuric acid solution, what is the normality of it? So once again, normality being equivalents per liter. We know that H2SO4, when it breaks apart, will eventually produce two H pluses and a sulfate. That means in terms of equivalence for every 1 mole of H2SO4, because I'm able to produce two H pluses, that will give me basically two equivalents of H plus. And since we do have the molarity given to us, 2.5 molar, which as we know is basically 2.5 moles per liter, we could use this once again as a conversion factor to convert us into normality. And in this case, we want to get rid of the moles. So on the bottom, we'll go 1 mole of H2SO4. Up on top, we'll go two equivalents. Here, the molarity, which are the moles, will cancel. And that will end us with a 5.0 equivalents per liter. Or you could just do 5.0 big N, kind of like what you do with molarity of H2SO4. Question on that there. I will say again, normality not doesn't come up all that much these days, and you don't really see it a lot. In industry, you still see it, but not too much. Probably you'll come across it. Maybe sometimes in 1A they do a titration where they want you to do equivalent weight or normality of your titration, stuff like that. So sometimes it does come up like in 1A. Any questions on that there? All right. So why don't you do this one? A solution contains phosphoric acid contains 50 grams of phosphoric acid per liter of solution. Calculate the normality of it. And hydrogen is 1.008. Phosphorus should be 3097. And oxygen should be 16. All right, so take a few moments, calculate the normality of it, equivalents per liter. We are looking for normality, which is equivalents per liter. We got 50 grams of phosphoric acid in 1 liter of solution. So really, we kind of have the bottom part there, which is 1 liter. So we do need equivalents, and we can't get equivalents from the formula. And again, here with H3PO4, we're looking at it breaking apart into three H pluses and a phosphate in this case. That means that we basically get 1 mole of H3PO4 will give us three equivalents here, as obviously we're producing three H pluses. Now, in order to use this kind of mole to equivalence relationship, I do perhaps need to convert my grams into moles. So we'll get the molar mass here, phosphoric acid. So 3 times 1.008 for our hydrogen, plus a 3097 for our phosphorus, plus a 4 times 16 for our oxygen. So we got 3 times 1.008 plus 3097 plus 4 times 16 gets us something like 97.99 grams per mole. We could use that to convert our grams into moles. So 50 grams of phosphoric acid, dividing by the molar mass here, putting grams on the bottom, 97, 99 grams per mole of phosphoric acid. Grams will cancel. So we can take 50 divided by 97.99. Going to get us a 0.510, and we'll call it 26 moles of phosphoric acid. We can now use our mole to equivalent relationship there. And if we do that, we will end up with here 0.51026 moles. And from here, we can see that for every 1 mole of phosphoric acid, we get 3 equivalents. So the moles will cancel, and that will get us here times 3, about 1.531 equivalents. So we have the liters, we now have the equivalents. So we can now go into our normality, and it would be 1.531 equivalents divided by 1 liter, which will give us basically that number right there. We'll call it equivalents per liter. Or again, you could put the big N back in, oops, at this point. Any questions on that there? Now, we do see sort of the opposite relationship. If we were to calculate the molarity of the solution, the molarity of the solution would be our moles, 0.5102 moles per 1 liter would give us 0.510 molar. You can see the molality versus the normality is a threefold difference because of the 3 equivalent difference between them. So also the molarity and the normality may be different if it is not a 1-to-1 relationship. If it was a monoprotic, both the molarity and the normality would actually be the same number as well. Any questions on that there? All right, so low normality, case it ever pops up, I suppose. There we go. That is the end of chapter. So the next chapter we're going to talk about is chapter 16, which is good because, we're running out of chapters at this point, I think. So we got to go to 17 and they're out. So that's good. So we're going to talk about acids and bases in this chapter. We're going to talk about things like pH, pOH, and the pH scale. Just a reminder of some of the stuff that we've talked about previously. Acids typically will have H plus in them, and bases typically will have hydroxide in them or be able to produce them. So when we talk about acids were first recognized by their sour taste. Vinegar's major component is acetic acid, which is a weak acid. Lemons have citric acid in them. Bases are characterized by a bitter taste. They also feel very slippery. A lot of hand soaps, drain cleaners, things like that. Those are base type solutions. Bases are sometimes referred to as being alkali. That is also why if you think about group 1 on the periodic table and group 2 on the periodic table, group 1 is the alkali metals. Group 2 is the alkaline earth metals. And pretty much, as I just mentioned a second ago, if you kind of hook any of those guys up with hydroxide, that's where a lot of our strong bases come from, which is, again, group 1 and group 2 on the periodic table, as I just wrote there in the last little bit there, lithium, sodium, potassium, calcium, strontium, and barium. Again, these guys with some hydroxide typically is where a lot of those strong bases come from. Hence the name of group 1 and group 2. Basically, those two names refer to it as being bases. So if somebody says you want to make it alkaline, that usually means you want to make it basic if you're doing something. Now, one of the first people to do a lot of work with electrolytes and really sort of explored acid and bases was Arrhenius. He basically gave a definition of an acid and a base, and he said an acid was something that was able to produce hydrogen ions in solution. So one of the important things to remember is when we're talking about something being an acid is that ability to produce that H plus in solution. And what we're talking about is the ability to produce basically kind of free floating H plus ions or hydrogen ions in solution, not attached to anything, just kind of freely floating around in the solution. Also, when we're dealing with acids and bases, there are a couple things in terms of H plus that we should be aware of, and that is H plus is oftentimes referred to as the hydrogen ion. In acid and base chemistry, it is essentially the exact same thing as H3O plus, and H3O plus is a polyatomic ion. It is known as the hydronium ion. And they are used pretty much interchangeable in acid-base chemistry. So you will sometimes see H3O plus in formulas. You also see H3O plus in reactions or equations. But you will also just as much see H plus in those formulas and H plus in those equations. So wherever you see an H3O plus, you pretty much could essentially kind of replace it with an H plus. Now, I will say books nowadays kind of roll a lot more with the H3O plus and kind of use them in formulas and equations. But I will also use H plus a lot. So anywhere I put H plus, you could basically just swap it out for H3O plus in formulas and also equations. The main difference as to why you would have, for example, H plus versus say H3O plus, it has to do with whether or not, for example, in your equation, you include water. So if we took, for example, an acid like hydrochloric acid, which is a strong acid, and I basically just wanted to write an equation of really just the hydrochloric acid breaking apart in water, basically. I could represent that with actually putting the water in the equation. And if I put the water in the equation, what's going to happen is we're going to actually see an H plus move that way. And we will end up with H3O plus and Cl minus. And really all this is showing is what happens when you put hydrochloric acid in water and how it breaks apart. Now you can very commonly and very simply kind of reduce that equation down to just the basic thing that's happening, which is hydrochloric acid is going to completely break apart into H plus and Cl minus. Both of these equations represent basically the same thing happening. And in one, because water was included, you get H3O plus rather than where you don't include water in the reaction. It's not really necessarily a reaction, but it breaking apart, you get H plus only. So they are equivalent to each other. And that's really the main difference of, why you kind of see H plus sometimes and you see H3O plus. They both just represent, if you took some hydrochloric acid and you put it in there, it is going to break apart into its ions. But one basically represents that when you do that, there's also water in there. So they kind of do a little thing, and that makes that H3O plus that's floating around in that solution. So they both really represent the same thing. H3O plus, H plus basically represents the acid part of the solution. So that's a way to kind of remember it. To further maybe not complicate things, H plus is also sometimes and very commonly referred to in acid-base chemistry as a proton. So H plus is also referred to as a proton. And that is because hydrogen has one electron, it has one proton, and it does not have a neutron, so it has no neutrons. So remember that when you become positively charged, you had to lose electrons to do so. So when hydrogen loses its only electron, the only thing left is a proton that it has. So sometimes it's referred to as a proton. So a proton, H plus, which is the hydrogen ion, and the hydronium ion, which is H3O plus, they all essentially represent like the acid part of what's going on in the solution. Any questions on that there? Now, a base is something that has the ability to produce hydroxide in solution, and it's the same idea. It is the ability to produce OH minus freely floating around in the solution. Once again, not attached to anything else, just floating around in that solution. And that is what something that is a base. Now, something like sodium hydroxide, which is a strong base, can easily do that because all it has to do is go for a swim and it will 100% break apart into ions. And basically, it's going to be a pretty big source of hydroxide ions. And it's going to be able to produce that pretty quickly. It is a strong base because essentially it's kind of carrying the hydroxide with it. So all it has to do is, like I said, kind of go in for a swim here, and it's just going to break apart into those ions and produce hydroxide pretty quickly. Now, not all bases actually have hydroxide in their formula. Some bases are able to actually produce hydroxide, and a very common one is NH3, which is ammonia. Ammonia is actually a weak base, and it doesn't have hydroxide on its sort of formula, if you will. But what it can do is basically suck out an H plus from water. And when it does so, it will create NH4 plus, which is the ammonium ion, and produce hydroxide. So although ammonia doesn't have OH on its formula, it could do a little bit of a reaction with water, and it's able to produce hydroxide, and it is still considered a base. That is also why it is considered a weak base, because it has to kind of do a little bit of work there to produce the hydroxide. And that's different than, say, sodium hydroxide, which obviously has hydroxide sort of on it. And it doesn't have to do much other than kind of go for a swim. It's going to produce that hydroxide. So um, that is sort of the difference there between a strong acid, a strong base, and a weak base. And I would say ammonia is a very, very common weak base. Any questions on that there? And there's a couple of our examples there. Again, how you make like hydrochloric acid is kind of, you can bubble some hydrogen chloride gas in some water and it will produce H plus and Cl minus, which is your hydrochloric acid. And once again, sodium hydroxide here dissolved in water will produce your hydroxide. Again, if you see on the right hand side of any arrow H plus or H3O plus, you should probably think it's going to probably be more of an acidic solution. If you see on the right hand side of the arrow like hydroxide, it most likely will be more of a basic type of solution because it's producing hydroxide. Now, the Arrhenius sort of concept of acid bases was really a good step forward, but it was limited in the fact that it pretty much only dealt with one type of base. He did a lot of work with bases that have hydroxide. And as I just mentioned, not all bases will actually have hydroxide in its formula. Something like ammonia, as we just saw there, can actually produce hydroxide. So that brings us to sort of the general definition of an acid and a base, and what is referred to as the Bronsted Lowry definition of an acid and base. And the Bronsted Lowry definition of an acid and base is an acid is a proton donor. And remember that a proton is H plus. So a Bronsted acid is something that can give away an H plus to something else, while a base is the one that's going to really accept that H plus. So a proton acceptor. So it will accept the H plus. So in the sort of Bronsted Lowry definition, you have an acid that's going to react with a base, and it is going to be the acid that's going to send the H plus over to the base, and it is going to accept that. Now, the result of that on the other side will create some partners and stuff that will be formed, and those are what are known as the conjugate base and the conjugate acid. And those are really the two things that are formed as a result of this H plus being transferred. Now, let's just talk about the H plus for a second, and it's something that people really kind of screw up on a lot. And they think about this as really just hydrogen, and they either maybe take off the hydrogen when they need to, or they add a hydrogen when you need to. But you also have to remember that it does have a charge which is positively 1 here. So if you lose an H plus because of the plus charge, you do become one more negative than you started with because you now have one less proton, more electrons. So you kind of become more negative than what you started with. So you do become one more negative than you started. And if somebody gains an H plus, you become one more positive than you started with. So let's just say, for example, we started with HCl and it loses an H plus, so an H plus comes off. This was going to leave us a Cl. It was neutral. You lost an H plus, you become one more negative, so that Cl gets again a minus as well. Now, if you had something like we saw with NH3 and it gains an H plus, so it's going to gain an H plus, the nitrogen, hydrogen will now become NH4. It was neutral and you gained an H plus, so you now become one more positive. So the charges here change from side to side, and that's really important. And again, it's a very common sort of error people make is not changing those signs with the positive charge on that H plus. Any questions on that there? All right, we're going to lay it up there for now.